Hello and welcome to today's lesson on fundamental interactions, which forms part of the particles and radiation topic in AQA A-Level Physics. So in today's lesson we're going to try and describe and define particle interactions using this idea of the fundamental interactions of the universe. So if we're successful and we learn in today's lesson, we should be able to describe what is meant by a force interaction, name the different types of force interactions, explain what makes charged particles either attract or repel each other, and finally describe an exchange particle. So in today's lesson we're going to look at the following part of the AQA A-Level Physics specification, 3.2.1.4 particle interactions. So there are four fundamental interactions in nature. You've got gravity, the weakest interaction in the universe, but it has an infinite range, and it's the interaction that causes the planets to rotate and for you to be attracted to the surface. You've got the weak nuclear interaction, an interaction that has a very short range, about 10 to the minus 17, 10 to the minus 16 meters, and closer it has a similar strength to the electromagnetic force, and it's the interaction that causes radiation in atoms. You've got the electromagnetic interaction. This interaction has an infinite range but only works on charged particles. It's the interaction that causes electricity, magnetism, charge attraction and repulsion. And finally we have the strong nuclear interaction. It's the strongest interaction in the universe. It has a strength about 100 times that of the electromagnetic interaction, 10 to the 13 times as great as that of the weak force interaction, and 10 to the 39 times that of the gravitational interaction. But it only has a range of about 1.5 times 10 to the minus 15 meters, and it's the interaction that holds nucleons and thus quarks together, but it only works on hadrons. So we can sum up our four interactions with the following properties. So you've got the strong nuclear interaction, which is the strongest interaction, but only has a range of 10 to the minus 15 meters. We have the electromagnetic interaction as our second strongest interaction. It's about 100 times weaker than the strong nuclear interaction, but it has a range extending to infinity. We then have the weak nuclear interaction, which has a range of 10 to the minus 18 meters, but has a strength 10 to the minus 7 of that of the strong nuclear interaction. And finally we have the gravitational interaction, which once again extends to infinity, but has a relative strength of 10 to the minus 36 of that of the strong nuclear interaction. Now just to clarify, the strength is how strong the interactions are compared to each other, and the range is how far reaching the interaction is. Now you must be able to remember the different properties of the different interactions for your examination. But what caused the different interactions to have different properties? What is the fundamental process going on? So let's think of this in terms of magnets and magnetic materials. So what causes the interaction between these magnets and magnetic materials, and why are they affected by each other even though they are not touching each other? Now Newtonian physics explains this concept by saying the objects were in a field. The magnetic field of each object interacts with the other object, producing a force. But what causes the field to exist? Now particle physics states that a force is produced by the exchange of something called a boson or exchange particle between the objects. This is what we call the interaction mechanism. Now the area of space which the exchange particle can travel is the size of the field. So the exchange particle produces this force field. So in this particular example, exchange particles are moving between the magnets, which produces the electromagnetic force between the magnets. So a force is produced by the exchange of a boson between objects in the universe. It's the fundamental interaction which produces the macroscopic force that we observe. So it's an important idea to note that this is the process behind how our forces exist in our universe. Now another name for an exchange particle is a virtual particle. Now these particles are referred to as virtual particles since they can only exist for a short amount of time. This is because the energy needed to produce them, the exchange particles, is borrowed from the universe. Now Heisenberg's uncertainty principle says that the change in energy times by the change in time must be smaller than Planck's constant. So what this basically means is energy can be produced out of the universe itself as long as it doesn't exist for a long period of time. Now we've looked at the idea of the conservation of energy before in physics, but the true law of energy conservation in quantum mechanics is that mass energy must be conserved over an average value of time. So the particles are referred to as virtual particles because they can only exist for a short amount of time. So what this means is, from Heisenberg's uncertainty principle, the larger the exchange particle, the more energy needed to be borrowed to produce it, so the shorter the time it can exist, so the shorter its range, the furthest it can travel, and therefore the field. So this means that if the exchange particle is massless, such as the photon, it requires no energy to be borrowed from the universe, so therefore it can exist forever, so its range is infinite, so the field it projects is infinite. So let's just clarify that the larger the mass of the exchange particle, the shorter the time it can exist, so the shorter the range of the force it produces. Now, in addition, the particles are called virtual particles as we cannot observe these exchange particles directly, because if a particle was observed by an experimenter, it would no longer produce the macroscopic force and would cease to exist. So we can only ever observe the effects of an exchange particle. We can't observe them directly. So it was discovered that forces occur in the universe due to the exchange of bosons or virtual particles, which we can also call exchange particles. These particles are virtual as they cannot be detected directly. If we intercepted them, we would stop the force acting. Now, the property of the virtual particle determines the property of the force it produces. So objects in our universe exert forces on other bodies as they exchange virtual particles or bosons. So it's an important idea. So basically, the scientist Hideki Ukawa theorized that interactions and forces between two particles were caused by virtual particles being exchanged between the two objects. He theorized that the objects were exchanging a particle backwards and forwards that carried the force and kept them together. And this is true of all fundamental interactions. Now, the general term for exchange particles is the boson, and they're fundamental particles like quarks or leptons. So the properties of exchange particle interactions leads to the properties of the forces. But just remember as well that as well as a force being produced, this occurs because energy and momentum are being transferred between the objects via this exchange particle, but the exchange particle cannot be observed directly. So you can think of virtual particles working a bit like two people on roller skates showing things to each other. So imagine that the two people on roller skates are representing two bodies experiencing a force. If person A throws a bowling ball to person B, A will slide back when they release it and B moves back when they catch it. So repeatedly throwing the ball backwards and forwards causes A and B to move away from each other due to the conservation of energy and momentum, so this interaction causes repulsion. This is like an exchange particle producing a repulsive force, as shown in the particular animation. Now, and imagine you have two people on ice skates or skateboards, okay, but now A and B are exchanging a boomerang, throwing it behind them, so it pushes A towards B and B catches it back from behind and moves towards A. So because you're conserving energy and momentum, this interaction would cause attraction. So the act of exchanging the particle has caused the attractive force. So bosons are virtual particles, particles which exist for a finite amount of time and space, and these particles cannot be detected, as otherwise the force they produce will not act and the particle would disappear. Now, in the standard model of particle physics, there are three kinds of bosons or exchange particles. The photon, which carries the electromagnetic interaction. The W and Z boson, which carries the weak nuclear interaction. And the gluon or the pion, it's a synonym, okay, carry the strong nuclear interaction. Now, the exchange of these exchange particles between objects in the universe causes the forces which we observe on the macroscopic level. Now, it's believed that the virtual or exchange particle for gravity is the graviton, but it is yet to be discovered due to the weak nature of gravity. Now, some physicists believe it's not been discovered as gravity doesn't work by the particle exchange interaction, but don't write that in your examination. The reason why we've yet to detect the graviton is because gravity is a very weakly acting force. Now, technically, Pions mediate the strong nuclear interaction between quarks, but we give it the name of a gluon when we're saying it's mediating the strong interaction between particles such as protons and neutrons. It's the same exchange particle, just different names are used at different particle levels. On the quark level, it's called the pion, and on the particle level, it's called the gluon. So to clarify, the virtual particles have different properties. The graviton is the exchange particle for gravitation, and this exchange particle has never been directly observed. The photon is the exchange particle for electromagnetism. This particle has no mass, so has an infinite range, so this means that the electromagnetic force has an infinite range. You've got the gluon, which is the exchange particle for the strong interaction. This is a massive particle, so it can only exist for a short period of time, so it means it has a short range of interaction, so because it has a short interaction, the force has a short range. And then you've got the W plus, the W minus, and the Z boson. These are the exchange particles for the weak interaction. Now there are 3 bosons for the weak interaction due to a really complicated reason. It's to allow the quantum isospin in hypercharge to be conserved in decays, which is degree level physics. Now the W boson is the largest exchange particle, so has the shortest range, so it can only exist for the shortest amount of time. So this means the weak force has a very short range. Now we also believe there's the Higgs boson, which gives objects mass, which was only observed in 2014. So when particles move through the universe, they interact with the Higgs boson. The more they interact, the slower they move, the more massive the particles. If the particle does not interact with the Higgs bosons, it has no mass, it can travel at the fastest possible speed. So it's important to note the properties of the boson dictate the nature of the forces. The W in Z bosons have mass, so have a short lifetime, so can't travel very far. So this means the W force, the weak interaction, has a short range, whilst the photon has a 0 rest mass, it has an infinite lifetime, it can travel anywhere, so the range of the electromagnetic force is infinite. So to clarify, the properties of the boson dictate the nature of the forces, and the properties of the particle interaction lead to the nature of the forces. Now in the 1960s and 1970s, particle physicists tried to explain their work on exchange particles and particle decays to the general public. Now when exchange particles are exchanged with particles, they can cause the particles to change type and cause them to decay. However, to their dismay, particle physicists soon realized that the general public just didn't understand how these exchange particles worked and what they did. So enter Richard Feynman, who is in the middle of his work trying to make physics understandable to all. So in Feynman's quest to make physics understandable, one of his greatest inventions was the Feynman diagram. Now these are diagrams used to describe and show particle interactions and decays caused by exchange particles. So in this example, the exchange of an exchange particle can lead to the particle changing type. Now it should be noted that the axes are not often drawn on Feynman diagrams and will not be shown through the rest of the presentation. And in addition, it's more conventional to depict antiparticles as normal particles but with their arrows reversed. So a Feynman diagram shows how 2 particles can interact and change over time in the universe. It's not a graph, rather it's a diagram to help people understand what's going on at the particle level. So let's have a look at what's going on. So in our previous understanding, we would have said that a force was causing a particle decay like a beta decay. So just to clarify before we move on again, okay, we've got our antiparticles on the bottom and at the top because the arrows are reversed. It looks like they're going backwards in time. That's not the case, it's just that they are antiparticles. Now our Feynman diagram will actually show the scale of time as well. So at the bottom of your Feynman diagram, you have the past, the particles before the particle interaction. Now just note, we show particles as straight lines on the diagram. We then move into the present, which is when the exchange particle is there to cause the interaction, and we show those as wiggly lines on the diagram, and then have the future, which shows the particles produced by the interaction. Now we have the following rules in Feynman diagrams. Time goes vertically up on the diagram and space is horizontal on the diagram. Particles are shown by normal arrowheads while antiparticles particles are shown by reverse arrowheads. If the particles are stationary, a vertical line is drawn. If the particles are moving, a slanted line is drawn. When a decay occurs and a boson causes an interaction, a wavy line is drawn between the particles. A wavy line will be labelled with the boson name. Now, the particles produced afterwards are often drawn as a label straight line. So the aspect of Feynman diagrams that students often struggle with understanding is which exchange particle is used and the direction to draw it. So to work out the boson used at each interaction, look at the following particles. If the interaction is causing attraction or repulsion, well, the force must be electromagnetism, so the exchange particle is the photon. If the interaction is between hadrons only and there's no leptons being produced, the force must be the strong nuclear, and the exchange particle is the gluon or the pion. And finally, if the interaction includes leptons and particles change type, well, the force involved is the weak nuclear, so the exchange particle is the W or the Z boson. Now note, the stronger the force, the faster the interaction. So this means interactions via the strong force are much faster than interactions via the weak force. So this is why alpha decay, which occurs via the strong interaction, is much faster than beta decay, which occurs by the weak interaction. Now you can also work out the charge of the W boson in the weak interaction by looking at the charges. So if you start off with a positively charged baryon and it becomes neutral, you can think that the particle is throwing away its positive charge, and it throws away its positive charge by having a positive boson, a W+. If the baryon is negative and then becomes neutral, you can think of it as thrown away its negative charge. So the boson would be negative, it will be the W-. If the baryon is neutral and becomes positive, we can think of it as losing a negative. So if the boson's negative, it's a W-. And finally, if it's neutral and becomes negative, we can think of the baryon as losing a positive charge. So the W boson will be positive, it'll be a W+. So here is an example of a Feynman diagram. Now remember, our Feynman diagrams show how particles change over time due to the interactions by exchanging an exchange particle. So here, the proton and neutron are attracted together by the exchange of a neutral pion. The particle decay is between two baryons, so we must use the strong interaction, so the exchange particle is the pion. No leptons are present, no particles change type, so it can't be the weak interaction, and because it's a strong interaction, it's a fast process. Here's another example. Two electrons repel each other by the exchange of a photon. Now the particle decay is between two leptons, but it must interact via the electromagnetic interaction because you've got attraction or repulsion. So in this case, the exchange particle is the photon. In this example, a neutron decays due to the weak interaction into a proton, an electron, and an anti-electron neutrino. Now this particle decay involves leptons and it involves a particle change in type, so it must be via the weak interaction, so it's a slow process. But if you think about it, you start with a neutral baryon, a neutron, and it turns into a positive baryon, a proton, so you can think of it that the neutron has thrown away its negativity, so the exchange particle must be the W-. Now in this example, a proton decays into a neutron, a positron, and an electron neutrino. Now it involves leptons and a particle is changed in type, so it's via the weak interaction. Now as it loses a positive charge, go from a positive proton to a neutral neutron, the W boson is taken away the positivity, so it's a W+. Now the fundamental forces and interactions are crucial to our understanding of particle physics. Now fundamental interactions allow us to understand if a nucleus will form or not, because the strong nuclear interaction holds the neutrons and protons together because they're both hadrons, and this is why proton-proton repulsion does not tear apart the nucleus. The strong interaction occurs between all hadrons, so all protons and neutrons, and in the nucleus it's the dominant force as it's larger than the electromagnetic repulsion and occurs over more nucleons. So the electromagnetic interaction causes repulsion between the protons only, because only the protons are charged in the nucleus. Okay, so that's a very important idea. However, unlike the strong force, there's no limit to the range of the electromagnetic force. Now, the interaction which causes radioactive decay in the nucleus to occur is the weak nuclear interaction. Now, the weak nuclear interaction is weaker than the strong nuclear interaction, otherwise it would affect all nuclei, not just the unstable nuclei. Now, interactions due to the weak nuclear force occur due to either the exchange of the W plus or the W minus bosons. Now remember, these bosons have a non-zero rest mass, have a very short range, 0.001 femtometers, femto 10 to the minus 15 meters, and are positive or negatively charged. So famous examples of weak nuclear force decays include the beta minus decay, the beta plus decay, and electron capture. So in this particular example, a neutrino, okay, a lepton can interact with a neutron, and antineutrons can interact with the proton. Okay, so if an electron comes from the nucleus, like in this decay, it can be considered to be a beta particle, and this comes from beta decay being identified as radiation before it's discovered to be an electron. Now, a neutrino, okay, can interact again with neutrons. So in this decay, a proton is given away its positive charge because it's going from a positive proton into a neutral neutron. So therefore, it's the W plus because the proton is losing its positive charge, and it's a weak interaction as it involves leptons and particles that change in type. So therefore, it's a slow process. In this particular example, it is carried out by the weak interaction because a neutron's turned into a proton. The particle is changing type, and it is also involving leptons, the electron and the antineutrino. Now it's a W minus because you start as a neutral neutron and go to a positive proton, so it's like the neutron has lost its negativity. Now again, it's a W minus. Now in this idea, the proton is turned into a neutron, so the particle is changed in type, so it must be the weak interaction doing this. Now it's a positive proton going to a neutral neutron, so therefore it is the W plus being used to carry this out. And occasionally a proton will collide with an inner shell electron, and this allows the W plus boson to turn the proton into a neutron and an electron into a neutrino. Okay, so what's happening in this decay? A proton is giving away its positive charge. It's going from positive proton to a neutral neutron, so it must be a W plus, and it's a weak interaction as it involves leptons and particles change in type, so it's a slow process. So to summarize what we've learned in today's lesson, there are four fundamental interactions: gravity, electromagnetic, weak and strong nuclear. The concept of exchange particles can be used to explain forces between elementary particles. The electromagnetic force has virtual photons as the exchange particle. The weak interaction, limited to beta minus and beta plus decay, electron capture and electron proton collisions, has W plus and W minus as the exchange particles, and we can use simple Feynman diagrams to show the above interactions in terms of incoming and outgoing particles and exchange particles. So if we've been successful and learnt in today's lesson, we can describe what is meant by a force interaction, name the different types of force interactions, explain what is meant, what makes charged particles attract or repel each other, and describe an exchange particle. I hope you've enjoyed today's lesson on fundamental interactions, which is part of the particles and radiation topic in AQA A-Level Physics, and have a lovely day.